What's up? Is P,
Uh,
P is going to be 3. P is the number of predictors.
oh, so beta 0 is not contained.
So you add in, so the reason we do P minus 1 is that P is the number of predictor values, and then we add in the minus 1 to keep up with the constant. So that's why usually it's denoted as N minus P minus 1, because P is like each actual predictor, and then you do the minus 1 for beta 0. So it's going to be N minus 4 on the bottom. It's N minus 3 minus 1, so N minus 4.
So where is it? Is that formula for S square?
This
Like
is S.
the
Where is this? This is just by
the
definition. So RSS is equal to the sum of this, the sum of the errors squared,
yeah.
right? And S
Oh,
squared is necessarily equal to sum of the errors squared minus N minus P minus 1. So
okay.
SI,
Oh, yeah.
yeah,
Got it.
RSS is equal to this. And then S squared by definition is this. So clearly, this is equal to RSS over N minus P minus 1. Does that make sense? And then
Yeah, yeah.
3, okay. And then for 3, the only difference is now the 95% prediction interval is given by, so prediction interval is now A transpose beta. So sorry, there should also be a T value here, right? Like a critical value. So T distribution, 0.95, whatever. I'm not going to, 1 minus alpha over 2. I'm not going to, yeah. So you have to put in, sorry, I forgot about that. It's going to be, again, A transpose beta plus or minus the T value. I'll just say T value times, and then it's the same thing, it's S, but instead of this, it's 1 plus that. So you added an extra S, basically. But it's pretty much the same. All you have to do is add in this extra 1 right here. Okay. Cool. So that was 7.4 point C. Let's cover the last one, so 7.7. Okay. 7.7. Okay. So we have this regression through the origin. So we're saying that yi is equal to beta xi plus epsilon I. And we have that, sorry, I'm just, expected value of epsilon I is properly equal to 0, okay? However, the variance of the epsilons of I is actually now equal to sigma squared times xi, okay? And we have I equals 1 through 10. So we need to find A. We need to derive the generalized weighted least squares estimated. Okay. So first thing to note, oh, sorry, and then also we know that xi is greater than 0. Okay, that's going to be important in a second. Okay, so in this case, we have, remember that yi is equal to beta xi plus epsilon I. And this is a problem because usually, remember, what do we usually assume? We usually say, okay, well, the expected value of epsilon I is equal to 0, and then the variance of epsilon I is equal to sigma squared, right? But in this case, we don't have that, right? We have that the variance of epsilon I is different, right? So we need to fix this. So this is actually a takeoff of what's called generalized least squares. So sometimes this will be written instead as, usually this will be just sigma squared times wi. So if you've ever seen generalized least squares, this is really what it is. It's just each value has different variance. So using that framework, because since I've done generalized least squares problems, I just kind of know what to do. What we want is we want the variance of just epsilon to be equal to the identity matrix. So right now the variance of epsilon, okay, as the whole vector is equal to like x1 through x10. And then I guess we're assuming these are zeros. It doesn't necessarily say, but I think we can assume naturally that they are, because otherwise you couldn't really solve this easily, at least. So we want this. This is what we want. And we have this. Sorry, this might be a little small, but I know you can't see it when I do this. So we want variance of epsilon is equal to identity. We have that the variance of epsilon is equal to this. So observe, however, that the variance of, okay, if I let this equal to V, okay, so sorry, let me it's larger. So V is going to be equal to this matrix, okay? It's the variance of the epsilon. Okay. Observe, however, that the variance of what I'm going to call V negative 1/2 epsilon, okay, which is going to be equal to V negative 1/2 V negative 1/2, which is going to be equal to basically this. So I'll define these in a second, but this is going to be the goal. So observe that this is going to cancel out this can we made it a matrix. So what is V to the negative 1/2, right? Well, if we let V to the 1/2 be equal to the square root of x1 through the square root of x10 down the diagonal, and then 0 as well, then we'd say the V of negative 1/2 would be this, 1 over the square root of x1 through 1 over the square root of x10, okay? So that would mean that if we multiply everything this by V to the negative 1/2, we get the proper thing we want, okay? Because then now, so instead we write the expression, instead of yi is equal to beta xi plus epsilon I, if we basically let, or I'll write this to a better way. So we let y is equal to beta x plus epsilon. If instead we write the expression v to the negative 1/2 y is equal to v to the negative 1/2 beta x plus v to the negative 1/2 epsilon, right? Then now we can let this be our error term, and then we now have that the variance, if I call this delta, then the variance of delta is now equal to the identity matrix, as we just showed, and the expected value of delta is still equal to 0. Okay. I think we can swap these. These two. Okay. And then from here, you can just actually solve for a generic least squares expression, okay? What I mean by that is instead of, as you can say that we're going to get that beta hat, I don't even know what, I've lost the thought of what the question was. Okay, yeah, we need to find beta hat. So remember, for standard linear regression, okay, you have that beta hat is equal to x transpose x inverse, x transpose y, okay? So if instead we let x be equal to v to the negative 1/2 times x, and y equal to v to the negative 1/2 times y, okay, we end up getting that beta hat is equal to v to the negative 1/2 x transpose, v to the negative 1/2 x inverse, v to the negative 1/2 x transpose, v to the negative 1/2 y. Which is going to equal to x transpose, and then notice that v is diagonal, so it's obviously symmetric. So the negative 1/2 v to the negative 1/2 x inverse x transpose v to the negative 1/2 v to the negative 1/2 y. We end up getting x transpose v inverse x transpose v inverse y. So that's beta hat, generalized least square. And you actually can simplify this further. Let me explain why. So if we look at this term, okay, so if we look at x transpose v inverse x, this is actually just going to be equal to, so it's like x1 transpose through, if we're looking at the columns, x, I guess I'll say L transpose, I don't know why I'm picking L. These are rows. And then V inverse, remember, is just 1 over oh, he has really bad notation for this. Oh, because there's only one thing. Oh, because, okay, sorry. So if you'll notice, okay, this is actually a lot simpler. Sorry. So if you'll notice, x is actually just equal to the vector x1 through x, I guess he uses x, what does he use, xn? Okay, xn, that's fine. Because we don't have any, we don't have an intercept. So the entire data matrix is just x1 through xn. So then we can end up actually simplifying a lot, because this ends up being x1 through xn times the matrix with 1 over x1 through x1 over xn, and then again times the vector x1 through xn. So you can get an actual value for this. Inverse, and then x transpose is again just a vector, x1 through xn, and then again v inverse is just a vector. There's just a matrix like this. And then y is also obviously just y1 through y. So I would run, I'm not going to finish this, but you can simplify this. That's kind of the easy part. You can simplify this into like something that looks very obvious. I won't say what you get, but now to find, what's the next question? To find the variance. The variance of beta hat, it's just going to be, obviously, it's just going to be the variance of x transpose v inverse x inverse x transpose v inverse y, which is going to be x. So this pulling this front out, pulling this whole thing, because this is all constant out in front. And the variance of y is just identity. So then it's just times this inverted, which is going to be, or transposed, which is going to be yeah. Oh, no, the variance of y, sorry. The variance of y is still v. Sorry, there should be a v here. Inverse, and then obviously that cancels out because you get these cancel out, and then one of this cancels out with this, so that cancels out, and you're just left with x transpose v inverse x inverse. Is there a sigma squared? Do they let you? Oh, it is sigma squared. Sorry. So there should be a sigma squared right there. Yeah, sorry. And then you again can compute this more directly by inputting the vectors in here. Sorry, so like convert to basically a summation using the vectors. Again, I'll let you guys do that. And then for B, it should be very obvious once you have what the formula is. Just as kind of a hint, the formula looks like, it's not necessarily the means. The means not directly involved, but you get the summation of xi and yi. That's all you need to know. So that's why for B, so sorry, I should say what B says. B says, assume the experimenter recorded the sample means. And they say, okay, attain a numerical value for beta hat GLS, basically. Or is it actually for the variance? Oh, so sorry, we want the variance and the beta hat value. And you can find both of those with only the summation of xi or yi. And it cancels out. So you get them, you'll see. So that's that problem. Again, I didn't give away all of it, but any questions about that one? Okay. Does anyone have any other questions you want me to go over? Or if either of you want me to go over just whatever other questions, like you haven't started it, that's fine too. You just say that. For the particular one, or no, no. Okay. Let me do, let's see. Well, I'm going to post this anyway, so I'm going to kind of anticipate what ones people will find difficult. I think let's do maybe do 7.3. Why not? Look at it. 7.3, which is given as 514 in the book. So if we look at 514, okay. So A, they say, okay, assume we have the columns, assume columns of X in Y is equal to X beta plus epsilon, where epsilon is just distributed normally with zero mean, are orthogonal. Show that beta I hat, beta j hat are independent. Okay, so this one's not too difficult, but all you have to remember is that the variance of the beta vector is going to be equal to sigma squared x transpose x inverse. Okay. So remember what x transpose x will look like. X transpose x is just going to be, so each of these we have basically the inner product between the positions it's in. So the diagonal would be like x1 transpose x1, x2 transpose x2, and so on to xn transpose xn, or really whatever. And so this one, for example, would be like x1 transpose x2, blah, 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 blah. Say x1 transpose x3, so on and so forth. So the inverse of these will obviously be, well, I'll explain why it doesn't really matter that we have the inverse. So if the columns of X are orthogonal, remember that means that, so if the columns of X are orthogonal, that directly implies that xi transpose xj is equal to 0 for all I comma j, I not equal to j. Okay, because that's what the definition of orthogonal is, right? The inner product is 0. So if you'll notice that if they're orthogonal, then all the off diagonals will be 0, right? So if all the columns of X are orthogonal, that means that all the off diagonals are going to be 0. So what we're going to get is something that looks like this. 0, 0. Okay, that's what X transpose X will look like. So remember, X transpose X inverse will also be a diagonal matrix, because that's how it works. This will be like 1 over X1 X transpose X1, all the way up to 1 over Xn transpose Xn, and these will all still be zeros. And then the variance, which is sigma squared times this, will have all these zeros here, right? And remember, since we have normal distributions, since these beta values are normally distributed, and this is what the variance is, it's necessarily true that if they're uncorrelated, then they are, because they're sorry, it's not just because they're normally distributed, they're multivariate normal. So because beta hat is a multivariate normal distributed vector, that means that if they are uncorrelated, then they do not have they're also independent. Okay. Next, okay, so let's say we have y is equal to x beta plus z and then some gamma plus epsilon. And we're saying that, so this is an extra term. So I believe that x is still orthogonal with each other. And we're saying z is also orthogonal to the columns of x. Okay. They say that show the estimate of beta in the expanded model is the same as the estimate in the original model. And they actually say that we don't necessarily need that x here. So they say that x doesn't necessarily need to have orthogonal columns anymore, which is true. I know that. So they're saying that basically what they want to say is that this beta value in here is equal to the beta value from above. Okay. So remember that in this expression up here, okay, something to remember, in this expression up here, beta hat was equal to x transpose x inverse, x transpose y. So this is what we want this new one to be. Okay. So to solve this, let's put these matrices together. So let's say that this y is equal to w times beta gamma, okay? And let's just let w be plus epsilon, and let's let w be equal to just x and then z. So it's like augmented. Okay, so it's x augmented with z. Okay. So now this goes back into standard linear regression, and we can just proceed with our process. So then we'd say that we know that this vector estimated, so beta hat, gamma hat, I guess, would be equal to W transpose W inverse W transpose Y. Okay. And this Y is the same as before, right? So then let's look at what Y is. So let's look at what this is. So this is going to be X transpose dotted with Z transpose times, again, X transpose Z, and then that whole thing inverted times X, sorry, there's not a transpose there, I don't know why I put that. X with Z, and then times Y. So again, let's simplify this. This is going to be equal to X transpose X right here. So if we just look at this whole matrix, X transpose X. This next term is going to be X transpose Z. This term is going to be Z transpose X. And then this term is going to be just Z transpose Z. But remember, inverse. So remember that Z is orthogonal to all columns of X. Orthogonal to all columns of X. So that implies that X transpose Z is equal to just equal to Z transpose X. No, that's not right. X transpose Z is equal to 0, and also Z transpose X would be equal to 0. Okay. So these are now 0. And that basically says we have, okay, well, this is going to be, and since this is a block, so then this is going to be 0, and this is going to be 0. And since this is a block matrix, we can bring this inverse individually. So this is really going to be like X transpose X inverse. And this is going to be like Z transpose Z inverse, and then 0, 0 times X, Y, sorry, Z times Y. And then this is going to equal to, if we look at multiplying these matrices, we get like first row, first column is just going to be X transpose X inverse Y, right? And then it's going to be this times this, which is going to end up being 0 again. Wait, hold on. Yeah. Yeah, and then it's going to be, oh, sorry, not y, x. Oh, wait, this is transpose. Sorry. That's why. Okay, sorry. I was like, what am I doing wrong here? Okay, wait, let me write this. So it's going to be this transposed. It's going to be x transpose c transpose. So it's going to be x transpose x. Yeah. X transpose x inverse times x transpose plus 0. And then the bottom is going to be 0 plus z transpose z inverse z transpose times y. I'll just put y both there individually. And notice that this is what you get for your beta hat value in this expression. And this is equal to beta hat from above. So they're equal. Any questions about that? So the person that just arrived, do you have a specific question you want to ask before I move on about homework, or was it just in general? Or
Can we go back to like 7.4 again? Like
okay,
for the confidence interval, we can calculate S scale, right?
you can, yes.
Yeah. So is that S or the square term of S that we need to use in the confidence interval?
It's you
Before,
have to use the expression that I used, which is going to be given by it's this. This is the expression you need to use. So you need S, or so this is for a prediction interval, and for confidence interval, you use S here as well.
okay,
So technically, you
so
could put S squared inside if you wanted to, but
oh yeah, got it. Okay.
okay. Well, let me finish out doing this problem. Or is that all this problem? Okay, and then it says blah blah blah. Okay, maybe I'll do a different one. Let's look at it's 5.9. Okay, so this is going to be sort of the idea is going to be from 7.2, which is also 5.9. Okay, so I'm going to actually do a question from a different thing that I've done, but it's similar. So this is similar to this one. So let's say you have some sort of price for houses. So you have over time. So Y1 through Y12 is the price for houses. Okay. Now, they want you to create a model that uses T as a predictor in some way. So, for example, if they said basically price is a linear function, and then they want you to specify y is equal to x beta plus epsilon, and they want you to describe, like, give x and then beta. Okay. For example, a price is a linear function of time. Okay. So to be clear here, t is going from 1 to 12. Okay. So they said, okay, price is linear function of time, you'd say, okay, well, y is equal to x beta plus epsilon. We'd say that y is still the same. So y1 through y12 would be equal to x. And in this case, x would be, that would mean like that y1 would be beta naught plus some beta 1 times 1. This is time, t. Y2 is equal to beta naught plus beta 1 times 2, and so on. Where this, again, is t. So you get, basically, you get y1 through y12 is equal to, we look at the beta naught variable, it's all ones. But the beta 1 is just going to be like 1, 2, 3 to 12. Okay. And then times just beta naught, beta 1 plus epsilon. Okay. So that's like a very simple example. And then the other thing you could say is like maybe price is a quadratic function of time. So 1 through 12 are just some time periods, right? They don't have to be that specific. I'm just letting them be like 1 through 12 just to make it a little simpler. So t is going from 1 to 12, which is also this. Okay, so that means that y is going to be equal to, just to be clear, beta naught plus beta 1 times t plus beta 2 times t squared plus epsilon. Okay, so you can just write that as, y is equal to x beta plus epsilon, and then x is now going to be still the ones for beta naught values, right? And then we're still going to have 1, 2, 3 through 12 for the beta 1 values. And then for beta 2, it's just going to be t squared. So it's going to be like 149 up to 144. Okay. And then we still just say that beta would be just beta naught, beta 1, beta 2. Okay. Next, let's say we have that there's some policy changes. My voice is cracked. At t equals 7. Okay. And changes the slope of the function. And allows for a sudden jump. So what that means is it's just going to look like this. So at t equals 7, some sort of policy changes, and there's some reason that we allow a sudden jump. Maybe it's over the time periods of like a month. And so if we were to do a month to a month, you could expect a dramatic jump, right? Because, there's a chance that you have enough time for things to change. So what that would mean is you'd have some sort of slope going here, right? And then at 7, you'd have like a sudden jump and the slope would also change, okay? So from 1 to 6, it's this line, and then from 7 to 12, it's this line. So how would I graph this? How would I write this as y is equal to x beta plus epsilon, right? Well, what you can do is write it like this. You'd say y is equal to, okay, it's equal to some slope for the first 7. So for beta, it's going to be like beta naught plus beta 1 times t, where t is equal to 1 through 6. And then it's beta 2 plus beta 3 t, for t equals 7 to 12. Okay. So if I were to make the X matrix, right? So let's look at Y1. So Y1 would just be beta naught plus beta 1 times t, which is 1, plus, and then I can write this as beta 2 times 0 plus beta 3 times 0. Same with Y2 would just be beta naught plus beta 1 times, again, t, which is 2. And then these both technically have zeros next to them. So on until Y12, sorry, Y7, and suddenly you'll get beta naught times 0. So now y7 is following this expression. So I get beta naught times 0 plus beta 1 also times 0, right? We're not using beta naught or beta 1 when we're at 7, plus beta 2 plus beta 3 times now t7. And so this would also just be like this, right? So for 12, it's zeros, beta 2, and then beta 3 times 12. And then again, you should express this now in terms of an x value. This would be, for example, 1, 1, 1s, and then zeros. So this is for beta naught. For the beta 1 column, we get 1, 2, up until 6. And then we get zeros. And then for beta 2, we would actually get zeros and then 1s. And beta 3, we get, again, zeros and then 7 through 12. Okay, so then what your homework actually asks is says, okay, what if we have this case where the slope changes at t equals a certain time, right? But they have to intersect, okay? So notice how these didn't necessarily intersect, right? But let's say we want to do it where we have that policy changes slope at t equals 7, but they intersect, but no sudden jump. What that means is that we have that from 1 to 7, it's some slope here. And then at 7, it's still here, but now the slope changes. Potentially it goes down, right? To 12. So let's write this as we just wrote this before. We say, okay, so y is equal to, okay, let's do the same thing we did before. Beta naught plus beta 1t for t equals 1 through 7, for 6, sorry. And then beta 2 plus beta 3t for t equals 7 to 12. Okay, but we have a problem here because this doesn't guarantee in any way that they're going to be colliding, intersecting at t equals 7, right? This is two lines with two different intercepts, two different slopes. So if you think about it, we have too many degrees of freedom, right? Like we have too many parameters for what we need to do. We have a constraint now that they have to intersect at t equals 7, so we need to get rid of one of the parameters because otherwise it's not going to work. There's too much variability, right? So observe that we need them to intersect at 7, which means we need beta naught plus beta 1 times 7 to be equal to beta 2, sorry, this should be a 3, beta 2 plus beta 3 times 7, okay? So we can specify any of these values and write them in terms of the other values, right? But I'm going to pick beta 2. So let's say that beta 2 is now equal to beta naught plus beta 1 times 7 plus beta 3 times 7. Okay, well, let's go replace this beta 2 with all these other values now, right? So we have this beta 2 right here. That would give, nope, sorry, minus beta 3 times 7. Okay. So if I replace that here, I get that now y is equal to beta naught plus beta 1 times t for t equals 1 through 6. And then beta 2, which is now beta naught plus beta 1 times 7. And then plus beta 3, and I'll just simplify it because it's going to be t minus 7, right? Because I have this minus 7 right here. So t minus 7 for t is equal to 7 through 12. Okay. So now I don't have beta 2 columns, so I don't need to make one. But if we can look at this, right, we have that we can just go through each of these, right? So we have a beta naught column, a beta 1 column, and then a beta 3 column. I guess really it's beta 2 now, but whatever. So if you notice for 1 through 6, we have 1s. And then for 7 through 12, we also have 1s. So we all of them have beta naught. For beta 1, right? Notice how it's t for this. So it's 1, 2, up through 6. I get to 7. Now it's time. They're all going to be 7. It's going to be 7, all 7. And then beta 3, so they're not in the first 6, so it's zeros. And then for the rest of them, it's t minus 7. So, I mean, you can either write, I'll just do 0, 1, up through 12 minus 7, which is going to be 5. And then our beta values would be also just beta naught, beta 1, beta 3, I guess I'll just keep it like that. Okay, I only have a couple more minutes. Does anyone have any questions about any of this? I don't know if I can do any other ones. Okay. Let me look and see if I can maybe give some help for a little bit. For 7.5, yeah, it's a multi-group ANOVA. Read section 5.3. So you're going to be using like within group and between group treatment, and it's an ANOVA table, so it shouldn't be difficult. 7.4, I think I went over some things about 7.4. For 7.6, there's a couple ways you can do it. You should note what the only way you're gonna be able to do it. So 7.6 involves rewriting SSR in a certain way. You'll have to note what is orthogonal to each other because there's going to be some expressions that are orthogonal, and you need to look back in your note to see what's orthogonal to make sure you can get that right. Otherwise, you're not going to get things canceling out properly. And yeah, that's pretty much it. Let me stop recording.